Okay, so I want to make this screencast to show you some of the basics that we've talked about conceptually for equilibrium and then introduce a couple of new concepts. Remember that equilibrium is unique for us because it's the first situation that we've dealt with where a chemical reaction can go forward and also backwards. And we call the point where those two rates, shown by these blue arrows, when those rates are equal, we say that the reaction has reached a state of chemical equilibrium. Now there's a couple of ways that we can visualize this. A common one from the PhET model is shown here in the graph where we look at amount over time. Let's say that we start with only reactant. So that means we start only with A and B. And let's say we start with this amount right here. Doesn't really matter how much, just know that we start with only A and B. And that means that we're not going to have any of the product AB, which I'm going to show in green. So the AB amount is going to be right here at 0, 0. So before the reaction starts, there's obviously only reactant. Now this isn't always the case, but just for this example. Over time, as soon as the reaction begins, we notice that the amount of reactant decreases as it's converted into product. And then at some point it levels off. Now remember that as the reactants are consumed, that means that the product has to be formed. So whenever we see one decrease, the other must increase. Now you'll notice there's a pretty clear line where equilibrium is established. And in this case, I'm going to draw a little dashed line to indicate where equilibrium is established. So you look at right at the point where the slope of the line becomes 0. And that's where we say, from this point on, we're in a state of equilibrium. Okay? So that's what we've covered up until this point. And in lab today, we covered some things that we can do to manipulate how the equilibrium position shifts by either adding more or less of something or doing something that removes a particular reactant or product from the situation. But I also want you to be familiar with some other concepts related to equilibrium that are mathematical in nature. Because if we can graph this information, we can also look for mathematical patterns and actually calculate amounts that will be present at equilibrium. So take, for example, this equation here. This is going to be an equation that we're going to use for a couple of examples here. This is an equilibrium reaction. We know it is because we see the double-headed arrow where hydrogen gas and iodine react to form hydrogen iodide. Now, if we're going to write what we call an equilibrium expression for this reaction, it's probably a good idea to have a general form first. So if you look at this generic reversible reaction here shown in blue, the general form for an equilibrium expression looks like this. KEQ equals, and then you take the products, the concentration of the products, that's what the brackets mean, raised to their coefficient, over the product of the reactants raised to their coefficient. So what you see here is this ratio, this equilibrium expression ratio, gives us some value, and this value, for all we know, it's kind of new to us, it's just designated as KEQ. Now this KEQ is actually very significant. It's a constant. What that means is, regardless of how much stuff we start out with, if we keep the pressure and the temperature constant for a particular reaction, the ratio given by this mathematical formula will always give us the same value. And that's pretty helpful. So now let's take this basic example and apply it to a real equation. Okay, so I want you to keep this in your head as we go to the next slide. So if I asked you to write the equilibrium expression for this equation, it's pretty straightforward. You'd start out by writing KEQ, which stands for the equilibrium constant, and that constant is determined by the concentration of the products, in this case there's only one, raised to the coefficient, so in this case we're going to square it because there's a coefficient of 2 in front of HI. And then the denominator, we take the concentration of hydrogen, there's no exponent because there's just a 1 in front of hydrogen, and then the same for iodine. So this is what we would call our equilibrium expression. And you can imagine that if we know the concentrations of hydrogen iodide, hydrogen gas, and iodine at equilibrium, we should be able to calculate KEQ. Okay, so once again, use this general format when you're looking at a reversible reaction in order to write an equilibrium expression. Now we can do more than just write expressions. We can also calculate the value of KEQ, that constant value. And so just for clarity, I'm going to use the exact same example that we just went over. So let's say that this equation at equilibrium has these concentrations. Hydrogen is 3 molar, iodine 1.5 molar, and hydrogen iodide 0.75 molar. Well, all we would have to do is plug the values in to our expression, which would be 0.75 squared over the product of 3 times 1.5. You simplify all that, and that tells us that the KEQ is 0.125. Now don't worry about units. In fact, in this case, there are no units for that equilibrium constant. Now, you might be wondering, well, what does this tell me? What's the significance of this? Well, it tells us a lot about what the reaction is going to do and what it's not going to do. When you see a K value that is greater than 1, that lets you know that you're going to favor the stuff that's on the top, which would be the products. So a K greater than 1 means that products are favored. Now if you have a K that's less than 1, like in our case, that tells us that the reactants are favored, which means those reactants aren't going to go and completely form products. So the sign and or the magnitude of K is very, very important in terms of our understanding of how far a reaction will progress at a particular temperature and pressure. So here's a couple of problems I want you to try. The first problem, I just want you to write the equilibrium expression for the Haber process. The Haber process is a process by which nitrogen and hydrogen are converted into ammonia. So take some time right now, and in your class notes, I want you to write the equilibrium expression for that particular equation, shown in green and underlined in yellow. Once you finish that, we can go on to the second problem. The second problem is, using that expression that you just wrote in problem 1, I want you to calculate the value of KEQ, given the 3 equilibrium concentrations shown. Make sure you show your work for this, and if you want an example, you can pause this video to get the numbers, and then you can take a look at the example that we had done here.